Hello everyone. So welcome to the week 4 of the live sessions for Earth Sciences for Civil Engineering part 1 and 2. Just please respond on the chat box if I'm audible and the screen is visible. Am I audible? Okay. Myself, Ananya Mukherjee, and I'm a fourth year PhD student in Department of Earth Sciences, IIT Kanpur, and Professor Javed and Malik from IIT Kanpur is taking this course on the NPTEL. So, with the live session that we have, so I will try to summarize what has been taught, and also if you all have any problems regarding the content or the assignments, you all can ask. And I'll also try to explain the different content that is already given to you as the assignment, and hopefully the slides and also my explanation is going to help you in solving the assignment for this week. So till now we have learned about the different components that make up the Earth's surface and also the Earth's interior. So we learned about the Earth's interior structure and a very basic about how certain things are formed on the surface of the Earth. Then we learned about minerals and rocks, how to identify them, how to classify them, and what are the different types of these components that are found. So now we'll move on to something that is very important in terms of civil engineering. That is the deformation that is seen on the Earth's surface, and the different geological structures that are formed due to the response of the Earth's surface to different stress conditions. So we'll try to learn that, and that is helpful as I've mentioned in the civil engineering projects and construction site identification and so on. So uh, over here we know that earthquake is actually due to the as a response to the different compressive or extensional stresses that are acting upon the earth surface. So suppose you have an unstrained crust, like it is at equilibrium, there are no different kind of stresses acting on it, and but there is a certain fault zone that is present. Now this fault zone could be, it was caused due to some previous stress conditions that was there. So the fault zone is present, so fault zone is a weak zone. Now we have a stress condition that is happening over there, formed over there. So due to this we'll have the stressed crust is going to respond to that kind of compression or extension. So in the graph in the right you can see that first you have the elastic deformation, then elastic limit, and then you have ductile deformation, and then you have a fracture, that is the the brittle condition where the material breaks off. So till in the second diagram over here, it is being stressed to the elastic limit, it is still not breaking. Okay, so it is still not breaking, and it can contain the strain over there, but after a certain point of time it will release the stress that has been caused, it will release the strain that has been accumulated, and it will relieve the stress over there. So due to this kind of deformation, this kind of stress relieving, different kind of waves are propagated within the earth's within the earth's surface and also on the earth's surface. So due this rupture, okay, this rupture over here, this is called an earthquake. So when earthquakes happen, we have two different kind of waves that are propagating within the earth surface, and also across the earth surface. You have body waves, you have surface waves. Now body waves, essentially p waves have they travel longer distances, okay, and so a lot of deep earthquakes, deep focus earthquakes, they produce p wave and s wave, and we had also already seen in previous lectures also that p wave and S wave are very essential to understand the Earth's interior structure, and that is due to this property of them, that they can travel longer distances. Okay, now surface waves are essentially, they propagate closer to the focus of the earthquake. So if you have very deep earthquakes, okay, so these surface waves, they cannot reach the surface. Okay, they attenuate, that is, they kind of slowly degrade as they are traveling from the focus or focal point of the earthquake. So, but if we consider shallow depth earthquakes, like the focus is within like few kilometers from the Earth's surface, these waves kind of cause the most damage when we talk about the damages caused by earthquakes. But that is because their motion is kind of the motion that they have, that is very destructive to the constructions and the other properties that are there on the earth's surface. So this is the elements of earthquake. So we can see the focus is where the rupture has taken place. Okay, like the rock blocks. Okay, you can see the line over here, that is the fault plane. Okay, so the rupture that has happened has taken place over here. So this is a focus, and after the rupture has taken place, the seismic waves are traveling. Okay, suppose you have a earthquake measuring station somewhere over here. So the waves will travel from here, and then they will record it over there. We'll see later on, the different kind of things that they record over there. Okay, and the point on top of the surface of the earth, okay, that is right above the focus of the earthquake, is called the epicenter. Okay, so any if suppose there are any uh, construction over here near the epicentral area, a lot of damage will be caused here. Okay, because the waves are traveling right towards the epicenter, and the area that is being affected is close to the epicenter. As we go away from the epicenter, the kind of the damage kind of decreases. Okay, because the waves that are propagating slowly they start attenuating as you go far away from the focal point or the epicenter. Okay, now how are earthquakes measured? Okay, so as I said before, there is an seismic station. Okay, they record the they record actually the travel time, okay, of the different waves that are propagating. So you have P wave, you have S wave, and then you have the surface waves. Okay, so seismogram is an instrument, and like a pen is freely suspended, and a roll of paper is kind of, it moves across. Okay, so when there is shaking or vibration in that area, so the pen is kind of freely moving. Okay, so the pen is in touch with that paper, and it starts plotting the the motion that is experienced by the instrument. So the first wave that is plotted is the P wave, because it is the fastest traveling wave. Then comes the S wave, and then the surface waves. Over here, R means the Rayleigh wave. Okay, so over here, as you can see, like there are two different magnitudes mentioned. So we'll see what are the magnitude scales. But over here, just this example kind of shows you that just from the magnitude of 6 to magnitude 7, the amplitude of the waves that are traveling is increasing. Okay, so that means actually a magnitude 7 earthquake is going to be much more damaging than a magnitude 6. Okay, so you can just understand, like the pen is moving very it's not moving very vigorously in magnitude 6, but when it's magnitude 7, it will move very vigorously, and that will be plotted in the seismogram that is presented over here. So this is how we measure, the kind of how damaging the earthquake is going to be. That all is going to be figured out from these, plots that we have on seismograms. Now, then we had the need to quantify the, the earthquakes that we have, the size, the damage, the kind of, effects that earthquakes have caused. So, in the start, we had the Rossi Forel scale. Okay, there were 10 degrees, and the degrees are, made based on the, the kind of effects that are seen. Okay, like suppose only maybe only trees are shaking or some shorter buildings are shaking, so this is how they quantified. Then later on Mercalli modified the scale and gave 10 degrees, and then later on Cancani actually modified the Mercalli scale to give 12 degrees. Okay, but the problem with the intensity is that it's based on the effects. Okay, now as I mentioned before, like the effects of the earthquake is much more disastrous and much more damaging when it is near the epicenter. Okay, but as you go away from the epicenter, the amount or the intensity of the damage caused by the same earthquake is going to be less. So intensity scales became very relative to the location of the, say, seismic station. One of the seismic station was probably, say, situated nearer to the epicenter, and one of the other one was situated far away. Now the effects that are seen at the two different seismic station will be different. So then you would have a difference in the intensity rating that they are going to give it. So that is why we have the magnitude scales. Okay, so the first magnitude scale that was developed is the local magnitude scale, ML. It was given by Richter, and then local magnitude scale was used pretty well to quantify the size of the earthquake. Okay, but then it could not quantify very deep earthquakes or the earthquakes with larger focal depths. Okay, then we had the two different wave magnitudes. Okay, so you have body wave magnitude and you have surface wave magnitude. Okay, so these were also used for a particular time, where they would quantify using the the surface waves and the body waves. Now, one of the advantages, as I mentioned, like as I explained, for the magnitude scales is this does not change with respect to the place. Okay, so that is why later on they kind of they could establish different empirical relations, which finally gave us the currently used scale, that is the moment magnitude, which was given by Hiro Kanamori. Okay, so it is based on this seismic moment. So what is seismic moment? Now the seismic moment is calculated based on the shear modulus of the crust. For crust, there is a constant value, but it depends. Like if there is a particular rock that is present over across a larger area, so you can also they sometimes use that also. So you have shear modulus, then you have the surface area of the ruptured area during the earthquake, and then you have the amount of slip along the fault. Slip is the suppose, okay, so what is a slip? Sorry. Is my screen not changing? Okay, yeah. So suppose this is the earth surface, okay, and we have the fault over here. This is without any stress. Okay, now suppose this block of the rock has moved down, okay, and then this block has moved on top. Okay, so now it will look kind of like this. Okay, so this distance, okay, this distance is called the slip of the fault. That is how much, this area, how much this rock block has moved with respect to this block. Okay. So that is how this seismic moment is, calculated, and with the help of the seismic moment you will get the moment magnitude. Okay, so this is the moment magnitude, and this is the formula. Okay, so suppose you're given you're given the area of the ruptured place due to the earthquake, and then you are also given the slip that has been calculated, gone on the site and seen. So then what would have been the seismic moment that was created by the earthquake? Okay, so you first convert the units into dyne per centimeter square, because even for moment magnitude we need the seismic moment to be in the CGS unit system. So you convert them, and then what you get is this answer, and then you use this to calculate the moment magnitude, and it is approximately 7.3 magnitude. Okay, now based on this moment magnitude and the different kind of moment magnitudes, Richter developed a scale which was compared to the modified Mercalli intensity scale. Okay, so that is how when you read the newspaper and somebody says, an earthquake of this much magnitude was had taken place, so it is a moment magnitude, and sometimes they also mention the intensity rating also of the same earthquake. So this is what we talk about, the seismic moment. Okay, so now we can get an idea about the size of the earthquake from the moment from the seismic moment and the moment magnitude scale. Okay, and now we want to know how much energy was released from that same earthquake. Okay, so that is why then another relation was established which links the magnitude. Okay, Richter magnitude means that moment magnitude, okay, and the energy that is released. So you can see that it is a logarithmic relation over here, and due to this, the nature of the relation, the each increase in the magnitude scale, like suppose the we are talking about a 5 magnitude, okay, and then we talk about the 6 magnitude. Now 5 and 6, it's increasing by only 1 in terms of the scale, but the energy is much bigger. It kind of amplifies. Okay, so we know that it is almost 31 or 32 times the the lower magnitude earthquake. So this is the kind of different how earthquakes are measured, what are the different elements of the earthquake that we require to know to kind of calculate the size, calculate the impact, and then understand what kind of what kind of constructions we need, what kind of building material we need. Okay, so all this kind of earthquake related information is kind of governs your choices in terms of civil engineering. So now we understood the different, the how deformation affects the earth's surface. Okay, now we'll learn about the different uh, kind of geological structures that have already suppose formed, due to this deformation processes that happen on the earth. Now for that we need to know something called the attitude of beds. Now what is a bed? Bed is nothing but you know suppose you go to a location, okay, and you can see there are different kind of linear material stacked on top of another. Okay, this is your say 0. Okay, so this is 0, so that is, this is the ground level, and then you're looking that there are different kinds of beds over here. Okay, now to understand, whether this kind of orientation of the beds is suitable for your construction or not. Sometimes we get even inclined structures over there, sometimes we get folded structures over there. Okay, so all these things actually kind of give an indication to the kind of processes that have taken place over there, or they might be taking place even now. Like, suppose for example Himalayas. Okay, so Himalayas, when you go over there, you can very easily see that it is very intensely deformed. Okay, and as we already know, the height of Himalayas is increasing every year, so that means those processes are still active. And we also know that Himalayas is very prone to earthquakes and landslides. Now these are all responses to the geological processes that are taking place even then. So that is why we need to know the orientation of the the rock structures that we see at a place. They indicate what kind of deformation is happening over there, and whether it's still happening. You can measure the changes in the orientation, you go after a while, or in those terms. Okay, so for attitude of the bed, we have two very important elements. One is the strike, that you can see over here is a red linear line. Okay, and you have the dip direction. Suppose this blue plate, okay, this tabular object that you see over here. Okay, so this is your bed. Okay, we are only considering one layer of bed, of layer of rock. Okay, and suppose I intersect one horizontal plane to this bed. Okay, this bed is at an angle compared to the horizontal. Okay, so we kind of imagine a plane over intersecting the bed layer. Okay, so where the imaginary plane cuts the rock layer, okay, it is going to produce a linear line. Okay, linear, the inclination of this line is 0 because it's an horizontal plane. Now this is called the strike of the bed. Okay, so this is a strike direction. Suppose your north is that side, so okay, so wait, okay, so huh, so your north is suppose like this. Okay, this, okay, so this is your north. So the strike direction of this bed will be from north, sorry, from north. What is the angle that is produced by this strike line? Okay, this line is also called strike line. So that will be your strike direction. So suppose this is 30. Don't look at this 30. Okay, this red 30. Okay, so we will say that the strike direction is north 30. Okay, so that is your strike. Now what is the dip? Dip is the angle measured in the vertical plane from the strike line that we have taken. Okay, so this strike plane, okay, this plane is over here. So now we see how inclined is the rock bed from this plane. Okay, so this is the angle of dip, or dip angle as we say. Now dip direction is always perpendicular to the strike line and always dipping towards the downwards. We don't take dip direction in the upper part of the bed. We take it in the downward direction. So over here we can see that the dip direction is mentioned over here. Okay, this is the dip direction and this is the dip angle. Okay, so now we know this is the red line is a strike line. We understood the strike direction, how you say it's not 30, and suppose the dip angle is also 30. Okay, so and the dip direction is say the dip direction will be southwest. Okay, I'll tell you how we understand the dip direction, and you can mention which direction the it is dipping in the later slides. So this is the strike and the dip of the bed, which is used for understanding the orientation of beds, understanding the orientation of the different geological structures, and also kind of helps you in understanding how you can uh, you know whether it's a good foundation or if it's not good foundation, for major geological structures, the areas that are with that. Okay, now we have two kind of dips. We have the true dip and we have the apparent dip. Okay, over here as we can see that the dip direction is mentioned. Suppose over here this is a very simple example. So over here suppose we have an instrument that is called Brunton compass. We can very easily place it on the inclined plane and kind of measure the dip direction. Okay, any dip direction or any dip amount that we measure that is exactly perpendicular to the strike direction is called true dip. And any of the suppose on top you do not get the exact plane, okay, the exact bedding plane that we have, or it's not smooth. So on field when we go we actually measure apparent dip. Okay, so apparent dip can be in any direction, any other direction, other than the true dip. Okay, any of these directions you can see. Okay, this is called the apparent dip. So now we move on to the different kind of geological structures that we see when we go on field. So the first that we see is fold. Now for the fold to have formed, suppose this purple line is your bed. Okay, so usually these are formed when you have compressive stresses. Okay, the bed is getting, or the beds, suppose there is a stack of beds. Okay, they are getting compressed. Okay, so due to the inherent property or inherent nature of these rocks, you will find different bends forming. Okay, we have two kinds of material. One is incompetent and one is competent. Okay, incompetent is it cannot take in ductile formation, as if you remember we had seen the graph on top. Okay, so incompetent is it it reaches its elastic limit and quickly it becomes a brittle material. Okay, competent is it can still take in the stresses that are being acted upon it, and it can bend and become a ductile material. So this is a very generic, like very layman language explanation of competent and incompetent material. Right now we are just going to see how these materials react to such compressive or tension, or sorry, compressive forces. So now we can see that when the folds are formed, okay, so these are called limbs. Okay, this is the limb, this is a limb, then you have this as a limb, and then this as a limb. So the fold is formed of limbs. Okay, and the where these limbs meet on top, okay, that is called the crest. Okay, that is a crest. And a hinge is actually the, sorry, the line. Okay, suppose this fold is also, suppose you have a longer bed. Okay, and this is how it's formed. So this linear line is a hinge, then over here this linear line is a hinge. Okay, so and then as we know in normal, like from one crest to another crest you have the wavelength of the fold that has been formed. Now we try to understand how these limbs differ and what are the different kind of the types of fold that we see later on. How are they going to be categorized? Now over here the limbs are dipping away from each other. Okay, over here then later on when it goes down, it will start when you reach the trough. Okay, so when you're reaching the trough, the limbs are dipping towards each other. Okay, then you have something called inflection point. Inflection point is a point on the limb from where the the dips are kind of changing. So over here you have away from the hinge. Okay, and now you sorry, yeah, this is away from the hinge, and now we see it is dipping towards the hinge of the fold. This is with respect to the hinge. Okay, the direction is kind of in the same way. Okay, the direction is the same, but the direction of the limbs dipping with respect to the hinge changes when we move from the crest to the trough. Now we can see that based on these elements of the fold, you can categorize the different kind of the folds that we see on field. So as when we are seeing, suppose we are understanding anticline. Okay, so based on the orientation of the limbs, we can say this is anticline. How? See the bed over here, it has folded. Okay, and it is forming a crest. So that means that limbs are dipping away from each other with respect to the, say, the hinge and the axial plane. Axial plane is like this is the axis of the fold. Okay, this is the axis of the fold and this is the hinge line. Okay, and the plane that is consisting of both the axis and the hinge line is called the axial plane of the fold. So now we see that uh, the limbs are dipping away from the axial plane. Okay, now for syncline we can see, suppose we draw the plane again. Okay, you have the hinge and the axis of the fold. Now we see that these beds are forming a trough and they are dipping towards each other with respect to the plane and the hinge. So then we classify it as a syncline. Okay, now based on the inclination of the axial plane, the inclination of the axial plane over here is it's vertical. Okay, so it is 90 degrees, so these are called vertical anticline, vertical syncline. You can classify it in that manner. Then orientation of limbs, I just said, if the limbs are dipping away from each other, it's an anticline. If the limbs are dipping towards each other, they are a syncline. Now stratigraphic position of the strata. Okay, to understand this, suppose these strata were first placed like this. Okay, this is your ground, 0. Okay, so when deposition was happening or when rock formation was happening, the one that is below, like the last one right on top of the ground is going to be the oldest. Okay, and the one on top over here is going to be the youngest. Okay, so the age of the rocks actually they increase from bottom to top. Okay, so now these horizontal layers, they got deformed by say compression. Okay, now that is why these anticlines and synclines are formed. Now when we are looking at the anticline, the rock that is at the center of the fold, okay, this place, okay, this is going to be the oldest one, while this is going to be the youngest rock, this gray part on top. This is youngest and this is going to be the oldest. Okay, now when we move on to syncline where the trough is formed, okay, now we see as per the shading that is given here, it is very evident that the oldest one is in the center of it. Sorry, this keeps happening. Okay, This is the oldest, and then this will be the youngest. Okay. So this is how you can, classify it as per stratigraphic position. Okay, now how stratigraphic position helps in, identifying whether it's anticline or a syncline. Suppose you're walking on the top of the surface, okay, and you can only see the limbs, okay. Now you cannot understand whether, they are dipping towards each other or they are dipping, away from each other. We will see one of the examples now, where you can't really understand whether they're dipping towards or away from each other. So that time, with other kind of stratigraphic age or determination, if the older one is at the center of it is at the center of the structure, and the younger one is seen the outside of the area, it is kind of over here. You can see that you see it is going from older to younger. You can say then that it is probably an anticline. And similarly, if you see that the strata, the rocks that we are kind of exploring, they are going from younger to older, then it is a syncline. This is how you can understand when you're on field. Okay, so this anticline, syncline, we saw how it can be classified based on the inclination of the axial plane, the orientation of limb, and the stratigraphic position. Now over here we have something that is called a plunging anticline. Okay, now anticline, because we can see the limbs are away from each other. Okay, anticline, we can see also, we can see that the older one is at the bottom and the younger one is on top. Okay, now we can see that the axial plane is still vertical. Okay, so it is a vertical, the axial plane is not inclined, so it's not an inclined fold. But we can see that now the hinge, okay, the hinge of the fold, that is this line of the fold, is now inclined. Okay, it is making an angle with the axial plane, the the horizontal line of the axial plane. Okay, so that is why this is called a plunging anticline. Now we come to another, that is a monocline. Okay, now monocline is caused that there is only one area where you can see an inclination in the beds, so that is why it's called a monocline. Now we'll see over here that we have symmetrical folds. Symmetrical folds meaning what? This is your fold axis. Sorry. Okay. So over here, okay. So you have the axis here. Okay. The angles that the limbs are making are equal. Okay, this angle and this angle is equal, so it's a symmetrical fold. And the axial plane is vertical. Okay, and stratigraphic position, this is going to be an anticline, then this is going to be a syncline. Okay, now in asymmetrical, we can see very easily that the axial plane is inclined. Okay, and the the angles made by the limbs are unequal. Okay, one limb is suppose say 30 and the other one would be 40. Okay, so it is called asymmetrical folds. Now this is an isoclinal fold. So now I was talking about suppose a kind of fold where you don't know whether they are dipping towards each other or away from each other. You see that these are dipping downwards. Okay, now suppose you can only see part of these folds. Okay, so you don't know whether dipping towards each other, they are dipping away from each other. Okay, so this could be one of the kind of default problems when we are encountering folds and we don't know. So that is why you use stratigraphics. So now we know that this is old and then this is young, and the axial plane is vertical. Okay, so it is vertical. So then you can know that this is a vertical isoclinal folds. Isoclinal why? Because the limbs that are there, you know, they are again same, okay, and the dip direction is same. Over here, as you can see that this is dipping in this direction and this is dipping in the other direction, okay. The directions are different for symmetrical folds, but over here both the limbs are, you know, dipping in the same direction. So that is why it's an isoclinal fold. Now similar way we have the overturned folds, okay. So in overturned flow folds, again you have that the axial plane is inclined and the limbs are kind of dipping in the similar direction, okay, but the dipping angles, like, you know, this is probably dipping in 20 degrees, this is dipping at, you know, say 40 degrees, okay. So then you call this overturned folds. Then you have recumbent folds. This is a kind of overturned folds only, type of overturned folds, but the axial plane is essentially almost horizontal, okay. And chevron folds are those folds where the crests are, you know, they are quite pointed, okay. You don't see this curved crest as you can see in this anticline symmetrical folds, okay. So these are pointed, okay, and this the axial plane over here is vertical, but it can be say inclined also, okay, but the chevron fold is classified based on the shape of the crest. Now here are some examples that we see, you know, on field, you know, when we visit different sites. Now over here you can see that the fold is, you know, going like this. Now we see that the limbs are dipping away from each other, okay. So this is an anticline, okay. Over in the second photograph you can see that, you know, you can trace out the curve like this, okay. They fold. Over here the limbs are dipping towards each other, okay. So this is a syncline. Over here we can see that, you know, the axial plane is kind of vertical, okay, and the limbs are kind of dipping in the same direction, okay. They are not away from each other or towards each other, okay. So this is an isoclinal fold. Now over here, as you can see, as I had mentioned before, that the crest that we are seeing is sharp, okay. This is your axial plane and this is your fold, okay. So this is a chevron fold. So these are some of the examples, you know, that we can see on field. Suppose this is, you know, kind of some exercises that we are seeing, when we kind of, you know, have to understand how to plot the strike direction, the dip direction of a folded structure, okay. Now over here we can see two views, okay. The top one is the cross sectional view and the bottom one is the map view. What is map view? Suppose you are walking on top of the surface in this direction, okay. You are walking along this direction and you encounter these different beds, say bed 1, 2, 3, 4, okay, then a fifth one, then you see that the third one is repeating again and then the second one and then the top one and the first one, okay. So you see when the beds are kind of repeating itself when you have walked off to a distance, okay, it generally means that we are we are kind of seeing a fold. A fold is present under this surface, okay. Now the top view is the cross section view, that is suppose you are looking at it, you know, from the side, okay. You are looking at it from the side. Over here we can see very easily, you know, that this is a fold, okay. It's folding like this and this is an intrusion, okay. So that has come from bottom. We had talked about igneous intrusions and different kind of intrusions and dikes. So this is a dike, okay. So this we can see, probably sometimes this is not visible also, you know, this cross section view. So we have usually the map view. Now over here we can see that this is the axial plane of the fold. Okay, this is the center of the fold that has been mapped over here. Why? Because as I said that we are experiencing 1 2 3 4, then the 4 is continuing, and then we have a very different kind of rock over here, which is formed in the like in the form of dike. Then you have the third again repeating, second again, and first. So that is why we are talking about, we can point out that there is an axis in between, and this is a folded structure. Now over here the arrows are away from the axial plane. Okay, now this we understand. Why? Because as per the ages that supposedly we might have calculated, this is the youngest, sorry, okay. Okay, so actually, okay, this is the older rock and this is the younger rock. How we can say this is that, suppose we keep joining these. Okay, we keep joining these, so we will see that the limbs are away from each other, and as per the ages that we have calculated, this is the topmost, and then the age kind of decreases, sorry, increases, age increases. That means this is the older rock. Okay, this is again younger and this is the older rock. So over here we can see that this would be the older one and this would be the younger one. So when the older one is at the center and the younger rocks are towards the outside of a fold, we call it an anticline. Okay, and over here we can see that the strike directions are mentioned. Okay, so the strike direction and the number, the value that is given here is the dip angle amount. Okay, is the dip amount of that. Okay, over here we can see that dike is almost perpendicular. Okay, it is close, it is very steeply dipping. Okay, so it is 80 degrees, so we mention that over here like this. Okay, now we come to the folds. We saw folds, which is you can generally see it where you have compressive stresses acting over there. Faults can be caused, the type of faults, there are different kind of type of faults that are caused due to the different stresses. Okay, over here these are some of the components that we measure when we are looking at a fault. Okay, so this plane that you see, okay, where lot of these things are mentioned, this plane is called the fault plane. Okay, if this is the fault plane, okay, so I'll draw a simple sketch here. Okay, so this is the fault plane, this. Okay, so the rock block that is above the fault plane is called the hanging wall, and the rock block, okay, that is below the fault plane is called footwall. Okay, so this is a very simplistic diagram. Okay, now suppose I make this into a total block. Okay, now this is your fault plane. Okay, we can see that the strike of the fault plane is like this. Okay, this is the horizontal line. Okay, and it will be, this is a strike and it is dipping like this. Okay, this is the strike and then this is the dip of the fault. Over here we can see that based on the movement of the fault, like it suppose the movement of the hanging wall. Okay, over here hanging wall, okay, it is, the movement is parallel to the dip. Okay, it is moving along the dip. Okay, it is moving along the dip, then it is a dipping fault, dip slip fault. Okay, or if it has moved, the movement of the hanging wall is towards the strike direction, it is called a strike slip fault. Over here we can see that it has moved along the dip, so this would be a dip slip fault. Now suppose you have fault, the rock blocks have not have moved both, parallel to the strike and also parallel to the dip, so that would be called an oblique slip fault. Okay, oblique fault or oblique slip fault. So over here as we see normal fault, okay, so the normal fault, this block has moved downwards. This is the hanging wall. Okay, so the hanging wall has moved down and it is in the direction of the dip, so this would be a this would be a dip slip fault. Okay, over here reverse fault. Okay, now if this is a fault plane, okay, over here the hanging wall has moved on top and the foot wall has moved downwards. Okay, now over here again the movement is along the dip direction only. Okay, over here like the dip is downwards but the movement is upwards, but it's still parallel to the dip, so this would be also a dip slip fault. Okay, a blind reverse fault is suppose the fault, the breakage or the the deformation has only happened below, and on top you just see a kind of a curvature that has been formed due to this fault. Okay, this fault plane has not reached on top, so this is a blind reverse fault. Now over in the bottom one we see that the movement of the rock blocks, okay, is along the strike of the fault plane. This is the fault plane. Okay, so this is a strike slip. Now when do we call it a right lateral, when do we call it a left lateral? Suppose you are the observer here. Okay, you are the observer here and you see that the right hand block of the rock is coming towards you after deformation. Okay, so it is coming towards you, the right hand side, so it's a right lateral strike slip fault. Okay, and suppose you are standing here, okay, and the left block is kind of moving towards you, then it's a left lateral strike slip fault. Why strike slip? Because the movement is along the strike of the fault plane. So this is a very basic understanding of what are faults, the kind of elements of faults that we need to know, and different types of faults based on the angle of the fault plane, the slip direction of the fault, okay, along the fault plane. So over here, suppose you see only the this huge fault. Okay, you can see that there is some movement along this, then there is movement along this. You see that there is a kind of discontinuity in the height or the surface level. So it is like this, then it's dipping, and then it's like this. Okay, so this is a normal fault. Okay, this is caused suppose one of the stresses is acting in this direction and the other stress was acting in this direction. Okay, so this is an extensional fault or normal fault. Okay, you can trace the fault very easily over here. Okay, and this plane that we see over here, this is also called as fault scarp. Okay, usually normal fault they can be from moderate to steep. Okay, steep angle as in this is the strike direction and this is the dip direction, and the amount of amount of the dip of the fault plane to the strike plane is the the dip angle that we are mentioning over here as 40 and 70. Okay, so a simplistic diagram would be this. Okay, this block has gone on top or not even moved properly probably, and this one has gone down. So this is the hanging wall of the fault and this is the foot wall of the fault. Okay, now a reverse fault. Okay, reverse fault, over here we cannot see the plane very easily, but we can easily identify that this would be the trace of the fault plane. Okay, this area is curved, okay, and this area is not, you know, curved with respect to this block. So we can say that this block has moved on top and this block has moved down, okay. And the fault plane is probably, you know, say suppose it's inclined like this. So this is your hanging wall and this is your foot wall. So how would this, you know, look like in a cross sectional view? It would look something like this, where this block has moved on top and this block has either moved down or it has not moved, okay. This is a reverse fault. Now generally these are, you know, sometimes very low angle faults, and there are some faults where the fault plane is, you know, just sorry, the fault plane is very low angle, okay. Don't consider this is, say suppose your you know, hanging wall and this is your foot wall, okay, and this is your fault plane, okay. So this angle is very low. When it is around, you know, 10 degrees or lower than 10 degrees, these are also called as thrust faults, okay. Thrust faults, you know, they are huge faults. Usually they appear as, you know, very huge faults. Some of the best example of thrust faults is seen in Himalaya, okay. So in Himalaya you have main boundary thrust fault, okay, which is a, you know, it is encompassing a huge area. So thrust faults can, you know, happen at very huge areas. Next we have lateral, oh, sorry, I have named both as left lateral. This is right, okay. I will change this in the uploaded slides, okay. Now how do we know that this is left and this is right? Okay, over here we can see that the road is getting discontinued somewhere over here, okay. It is discontinued, okay. Now this has moved towards this side and this part of the road has moved this side, okay. Now this person is standing here, he is looking at this fault plane, okay. You can very easily see that the sense of this block is towards him. This is the left side, okay, when he is standing here, okay. So that is why this is a left lateral strike slip fault, okay. Now if even if the person was standing here, okay, still he would see that the left hand side block is you know, is displaced towards him. So it's a, whichever side you're standing of the fault plane, the sense is not going to change. That is why this is a left lateral fault. Now over here we can see this is a right Y, okay. You're standing here, you see that this has been displaced this side, this part has also been displaced this side. If you're standing here, this is your right side, okay, and the left side has been displaced that side, okay. So the sense is again the right side, the right block is moving towards you. So that is why this is a right lateral strike slip fault, okay, not left. So this is how you identify faults, and you know, you the type of faults that you see on you know, when you go out to these geologically important areas, or suppose you're you know, kind of constructing any construction which you kind of, you know, place right on top of the fault plane is going to be you know, it is going to be weak. It is not going to be a strong you know, construction, okay, because you don't know when a movement, you know, can take place along this fault plane, okay. And you can't even build it like this, you can't even build it like this, okay. You can build it on this side or this side, okay. So the damage won't be, you know, through your construction. Obviously if there is a, you know, larger earthquake across this fault plane, there is going to be some damage, okay, but that is again, you know, relative. This is a very simplistic understanding, you know, how identifying fault planes and kind of mapping the fault planes is going to help you. Suppose, as we had seen in the, you know, fold structures, suppose this is your map view and this is your cross sectional view, okay. So you're walking on your, on the surface in this direction, okay. So you find that you see G and then you see F, sorry, F, bed, then again you see F bed, and then again you see the which bed is this? This is E bed, and then you have the D bed. Okay, so A, B, C, D. So A is the oldest and D is the youngest. Okay, as per the we see that if this were horizontal, A would be the lowest, and G would be the topmost rock layer. Okay, so now when you're walking across, okay, so you encounter G, F, then you have F bed again, and then you can see there is a there's a discontinuity on top, okay, which is the fault plane. Then you see there is a dike again, you have the dike, then you again see E bed and D bed. Okay, so this is the fault plane you have mapped. Then you also mention the dip direction and the dip strike. Okay, so this say G is dipping this side, then even F is dipping this side, even E is dipping this side, so all the directions will be in that sense. Okay, strike direction and the dip direction. Okay, and the amount over here it's 30, then this is F is 60. Okay, then sorry, not F, F is also 30. Okay, and then the dike is say 85, so you write over here 85. Okay, now the fault. Okay, now the fault direction you cannot see on top. Okay, how will you know the fault direction? Again, understanding, if you are moving from the younger beds are exposed over here and older beds are exposed over here. Okay, so you can say that this has moved downwards. Okay, why? Because over here you cannot see that this has been exposed, this is not exposed over here, but this is exposed over here. Okay, so this has moved downwards and this has moved tops, and this is the fault plane. So the top block, that is the hanging wall, has moved downwards, so that is a normal fault. Okay, now we come to stereo net projections. Stereo net projections are required to kind of understand how you can you need to represent these fault planes, these fold axis, fold axial planes. Okay, you need a kind of 2D representation of these 3D structures. Okay, now it is not very easy to always find this cross section, and then you find such nicely layered beds everywhere. Okay, it's not in reality it's very difficult. So what we do is, suppose as I had shown you, you can see the fold. Okay, you can see the fold like this at the side. Okay, and you can see that, suppose this is the axial plane that you can understand. Okay, now the axial plane, you also kind of measured its strike and dip. Okay, you have gone on top of the fold and you have seen this. Okay, now you know the strike and the dip direction of this plane. So now suppose you consider this entire thing as a plane. Okay, you take the plane, and this is a sphere and this is a hemisphere. You kind of intersect the hemisphere with this plane. Okay, wherever this plane intersects and makes this curve. Okay, this can be projected on this horizontal hemispherical, this circular plane. Okay, this will be like this. Okay, every point of where the plane is intersecting the hemisphere can be projected on top of this horizontal plane. Okay, now this plane can be converted into a stereo net, that we will see after this. Okay, suppose this is your stereo net. Okay, now in this stereo net, suppose you have to plot a plane, that is strike direction is mentioned first, and then your dip amount, sorry, this is the dip amount and this is the dip direction. Okay, southwest is the dip direction, 70 degrees over here is the dip amount, and north 310 degrees is called the strike direction. Now suppose you're given this stereo net, okay, so and you layer it, you lay a tracing paper on top of the stereo net, okay, you can print this out in an A4 size sheet, okay, and then you can lay a tracing paper on top of this, okay. So suppose you have layered a paper, okay. What you do first when that paper is, you first mark the north, the east, the south and the west, okay. You mark this over there, and then you also, you know, mark the center. Now in a stereo net, the degrees, okay, the angular divisions increase, okay, towards the inside. So this is 0, then this is 10, then 20 at 10-degree intervals, and the center line is actually 9, it's actually 90 degrees. Okay, so the center one, 90 degrees, okay, the center line. So you first plot the 4 different directions, okay, then you see where is your north 310. So this is your north 310, okay. So your strike direction, the plane is going to strike in this direction. So once you have found your north 310, you take this point towards your north, okay. So then you mark the 310 on top, okay, it is already marked, it is in the north, and then you also mark the south point, keeping the north 310 in the north point, okay. Now when you say 70 degrees is dip, okay, so you start keeping the north 310 at north position. You start counting from the, you know, you see that it is southwest, okay, so you know that it is dipping on the other side, okay. When so from this side you start counting 0, 10, 20, 30, 40, 50, 60, 70, okay. So your plane will, you know, kind of look like this after you have plotted. It's not exact over here, but it will fall right on this big line, big curve, okay. And then once you have plotted the plane, okay, you take it back to the north 310, and then you will see that once you have plotted this, okay, suppose it looks like this, and this is the 70 degrees and this would be the dip direction, okay. So this is how you can, you know, represent a plane on the stereo net. It is a bit difficult to, you know, show it online, but you can find videos, and you know, you can try to see how they do it. It's simple, it's just you know, understanding the steps that you take. First you mark the strike point, okay, one of the points of the strike, then you take it to the north of the stereo net, okay, then you see how much is the dip amount. You start calculating it either from the west side or the east side depending on your dip direction, okay. And then once you have found your dip amount, you take that as the these lines that you see, the horizontal curves are called greater circles, and the the vertical you know, the vertical curves are greater circles, and the horizontal curves are the smaller circles, okay. So this is a great circle and this is a smaller circle, okay. So once you know your dip amount, you start calculating the greater circles, okay. 0 at the edge, 90 in the on the middle greater circle, okay. So you plot your dip amount, then you trace out the plane, the you know, the entire plane along that greater circle, and then you revert it back to your original strike direction point. So that is going to be your axial plane, okay. Fold axis, or maybe even fold axial plane or the fault plane, okay. And even you can understand you know, how much the fault is dipping and how much you know, the fold axis fold plane is dipping. So that is, then you can classify what kind of you know, fold or fault it is, Okay, and even for folds, you will have you can trace out the the limbs of the folds. Okay, this is suppose the line that we have drawn over here, this is one of the limbs. Okay, say another limb that you have traced out, it's like this. Okay, suppose you cannot understand where's the actual plane, okay, the fold, so you have the two limbs, you kind of get the strike direction, the dip amount and the dip direction of the limbs of the fold. Okay, and you have two. Okay, and so the point where they meet. Okay, so the point where they meet, that is going to be the hinge point. Okay, hinge of the fold. So these are some of the things that you can understand when you are representing such structural elements on top of the stereo net. So there is another example that I've put over here. You can just understand uh, on the slide itself, or some or just take a paper and kind of see how you can uh, trace this out. So you can solve this on your own. This is something that it will help you understand better how these geological structures can be represented and well understood. You cannot always go over there and see the entire structure in its original form. It has been deformed, it has been re-deformed. Okay, so these are ways where you can understand even the the deformation processes that have taken places, the stages of deformation that has places. You can also plot multiple deformation stages using the stereo net. So the stereo net is very useful to understand geological structures. So for today this is it. Hopefully it helps you. If you have any question uh, or any thing that you want to uh, anything that you would want to ask right now, you can ask now obviously, and if not, I will send one doc form link on the chat box. You can use it. Okay, the Google Slides link is also there, and also the YouTube channel where the recorded lecture for these sessions is already up for the last weeks, and today's will be uploaded by tonight, and the Google Slides will link will also be updated by tonight, and all the previous live session slides are in the same link. So just follow with every week. It starts from week 1, then it goes the latest ones are uploaded and updated in the below slides. So use the feedback form if you have any question. I will try to answer it either in the discussion forum, or I can also explain it in the next session. So if anybody has any question, you all can just ask right now. So if you don't have any questions, so I'll end the meeting here. Thank you for joining. Hope to see you next time again. Okay.